Hi everyone! Today let's talk about section 14.6, surface integral. We have studied integrals on interval, on region in the plane, on solid region in space, and along curves in space. Okay, one situation is still unexplored. Okay, so what is that? Well, in Cal 1, integral on interval, that's like we have a single integral, right? On region in the plane, well, on region in the plane, it's like we have a double integral over region, right? Or solid regions in space, well, that's the triple integral. Right, and along curves in space, well, that's like the line integral. Okay, and so we're still missing one situation. Okay, so suppose a sphere like the Earth has a known temperature distribution. Perhaps it is cold near the poles and warm near the equator. How do you find the average temperature over the entire sphere? Okay, and we mean the surface of the sphere, not the inside. Okay, so we should add up the temperature values over the sphere and then divide it by the surface area of the sphere. How do we integrate a function, let's say the temperature function, over a surface? This question leads to surface integral. So in order to learn surface integral, we must first to talk about the parameterization for a surface. So a curve in R2 is defined parametrically by R of t equals x of t, y of t. So this is one-dimensional. Right? It requires one parameter and two dependent variables. Okay, so this is a curve in the xy plane, right, of t. Stepping up one dimension, to define a surface in R3, we need two parameters and three dependent variables. Okay, so R is now a parameterization from R2 to R3. So let me draw the picture here. Okay, so let's call the variables, the independent variables, be u and v. Then let's say u is between AB, v is between CD. So we have this rectangle, and then we get the R map this rectangle into a surface in a space. So a space like that, S. So this is x, y, z. Okay. Yeah, so R is defined over a rectangle in the UV plane as the parameters UV varies over a region R, a rectangle R. Then the vector, sorry, abuse of notation. Small r is the parameterization. Big R is the region, the rectangle region, okay? So the small r, the parameterization, swaps out a surface S in the space. So this is the picture. So far, so good, everybody? Okay. All right. Here we have some examples. Let's look at each example. First, we have cylinders of radius A and height H. Okay, what does that look like? Well, we have cylinder. Okay, so height is H. Let's imagine that's the origin, and this is x-axis, y-axis, and z-axis, right? And here bottom, the radius is 8. So we are on the cylinder, okay? So for rectangular coordinates, x equals a cosine theta. So a and h, they are constants, okay? And so x equals a cosine theta and y equals a sine theta, okay? And then Z is some values from 0 to h. Okay, theta is between 0 and 2 pi. So far, so good? Okay. Now, to find the parameterization, well, we think about a point on this cylinder, right? So here, what is changing? You can see the angle is changing. So theta is changing and z is changing. So we can let u be theta and let v be z. Okay, then we will get the x is now become a cosine u, y becomes a sine u, and z becomes v. Right? So this is R of UV. Okay, so this is our new parameterization. So far, so good, everybody? Okay, let's continue. Next, we have cones of height h, radius a. All right. What is that? Okay, so let's draw a cone. Oops. Let me see. Let me draw a cone. So let me draw a cone here. Okay, so we're on this cone, and let's say here that is A and that's H. Okay, and then on any point of this cone, okay, so how do we figure out the coordinates? Well, here, suppose we have the cylindrical coordinates, we have R and theta and z, right? So we can imagine this guy and then, okay, let me draw better. Let's say if this point is here, okay, then here is R. So far, so good. So if we project this guy down here, that guy is theta. Alright, z is this guy. Okay, so if we want to use the rectangular coordinates, okay, in rectangular coordinates, we're gonna have x, y, z, right? And x equals r cosine theta, but here we can figure out the r. So what is r? Do you see there are two triangles that are similar? Then the corresponding sides have the same ratio. So r over z equals a over h, right? Okay, so r is then a over h times z. So x is r cosine theta, so a z over h cosine theta. Y is r sine theta, so a z over h sine theta. And z is z. Okay, so and then we can let z goes from 0 to h, and then the angle theta goes from 0 to 2 pi. So now, in order to write the parameterization, we can let u be theta and let v be z as well, right? Then we have x's a z is v, so a v over h cosine u. Y is a v over h sine u. And then z is v. Okay, so now you see this is our parameterization. And v now is between 0 and h, u is between 0 and 2 pi. So far, so good, everybody? Yeah, you can kind of think about the parameterization R. It maps a rectangle from the UV plane. U is between 0 to 2 pi. V is between 0 to h. We map this guy onto this cylinder is this guy. Can you imagine? And here as well, Okay, so we also have 0 to 2 pi h, and we have this guy mapped to O, this cone. So far, so good, everybody. All right, let's continue. Okay, how about spherical coordinates? Well, spherical coordinate, you can see rho is rho is constant, right? And if we want to write it as a rectangular coordinate, what do we do? Okay, by the way, for the parameterization for surfaces, usually we use the rectangular coordinates. Okay, let's see. Here, if we express the spherical coordinate in terms of rectangular coordinates, we have x's rho, sine, phi, cosine. So rho is a, and then we have sine phi, cosine theta, right? Y is a, sine phi, and sine theta, because the r is a sine phi, right? And z equals a cosine phi. So far, so good. And what does the sphere look like? So sphere, we have the circle and the top here. Okay. For a point on the sphere, phi is the drop down angle. If we project this point down, here is theta. Okay, and this length is r. Okay, so far so good. Okay, now what do you think about let u to be? So you can see the variable are phi and theta. So we can let u be phi and let v be theta, or you can let u be theta and let v be phi. We just have a different parameterization. Then in this case, you can see x is a sine u cosine v, y is a sine u sine v, z is a cosine u. Alright, now u is like phi. Phi is between 0 and pi. V is like theta. Theta is between 0 and 2 pi. So that corresponds on the uv plane. U is from 0 to 2 pi, and u is from 0 to pi, and v is from 0 to 2 pi. Okay, so far so good, everybody. Okay, so now let's continue. Look at the following example. We want to find the parametric descriptions for the following surfaces. First, the plane 3x minus 2y plus 5z equals 2. Okay, so we know it's a plane. We can let two of the variable free and then express the remaining variable in terms of the other two, right? So let's say, okay, let's express z in terms of x and y. Well, then we move the 3x on the other side, it becomes minus 3x. We move the 2y on the other side, it becomes plus 2y. And then we divide it by 5. Right? Now we can let u be x, v be y, and then z is gonna be 2 minus 3u plus 2v over 5. So what is our parameterization? Okay, r of uv is, okay, x is u, y is v, and z is 2 over 5 minus 3 over 5u plus 2 over 5v. Okay, now u and v can be any number, real numbers, right? Because it's a plane. It can be far away, right? It can extend far away. So u and v are any real numbers. So far, so good, everybody. You can also let y be u and z be v, and you can solve x in terms of u and v. Or you can let x be u, z be v, and solve y in terms of u and v. Okay? So for a surface, we can find many different parameterization for it. Okay, B, the paraboloid. Wow, you see, z is already a function of x and y. So the natural parameterization is to let x and y be uv. So let's see here. Here I want to do different permutation with u. So first we can let u be x, v be y, right? And then z is just 4u squared plus 4v squared. So far so good, everybody. And here we have a problem because we have restrictions. So let's see here. So when we draw it, this is a paraboloid. Okay, z is between 0 and 9. Okay, if z equals 9, we get 4x squared plus 4y squared equals 9. X squared plus y squared equals 9 over 4. So which means this is a circle with radius. So if we project down, this is a circle with radius 3 over 2. Right? Okay, so this is a paraboloid. Yes? Okay. So, but the problem is if we let z be 4u squared plus 4v squared, and because z is between 0 and 9, which means if I project down here, there is a region of u and v, so there is restriction on u and v. Can you imagine, everybody? So, yes. So how do you describe this region? Well, because it's a circle, we can let let's see, we can let u between minus 3 over 2 to 3 over 2, but then v will be between negative square root of 9 over 4 minus u squared, and then the positive 9 over 4 minus u squared. Okay, so you can see the v, the boundaries v depends on u in this case. Okay, so this permutation is not so good. Let's look at another permutation. Yeah, in order to calculate and easy for us to calculate, it's better to have the u and v, the values are between two constants. Then we have a rectangle in the uv plane. So second, think about it. 4x squared and 4y squared, it looks like a circle, right? Then we can try to use cylindrical coordinates for it. Okay, so let's see here. So if we express x squared plus y squared, this our parabola, we get z over 4, right? Then by the polar coordinate, well, this guy should be r squared. Then now we know r squared is then square root of z over 4, so that's square root of z over 2, right? And then we know x equals r cosine theta and y equals r sine theta. So far, so good, everybody? Okay, so the one way is we can let u be theta, and then we can let v be r. Well, in this case, x will be v cosine u, and then we have y will be v sine u. So far, so good, everybody? And how about the z? Well, what's the relationship between z? So we want to express z in terms of r. Well, we can look at here. Solve for z. So z is then 4r squared. So we have 4r squared. That is z. Z equals 4r squared. Okay, so now the abuse of notation. Okay, so that's why let's call it gamma. Let's don't call it r. Yeah, sometimes I use gamma, sometimes I use r, because in Word type r is easier to type gamma. To type gamma, I need to go up and insert equation or symbol, and then I need to pick the Greek letter gamma. So that's why I usually start with gamma, and then when I type it, sometimes I change it to r. It's because it's easier to type in the word. Okay, but here, in order to avoid abuse of notation with the radius r, so let's call this guy gamma. Well, gamma is then x is v cosine u, y is v sine u, and z is 4. Oh, you know, r is v, so 4v squared. Okay, what is the good thing about it? Well, the good thing about it is now u is like the theta, so u is between 0 and 2 pi. Let's see. And v is the r. Okay, you know, r is square root of z over 2, but because z is between 0 and 9, so r will be between, so keep in mind, r is like square root of z. So if we plug in 0, square root of 0 is 0. And there, square root of 9 is 3. So 3 over 2. Oh, that's r, and r is v. Okay? So now you can see u and v, they are between two numbers. Yay! Then I got my u 0 to 2 pi, and my v is 0 to 3 over 2. So we get a rectangle. And this parameterization is good. We don't want the previous one, because you see your v is not, your v depends on u. That's not good. So far so good, everybody. That's why when you see like x squared plus y squared, this is like a circle, then think about the polar coordinate or cylindrical coordinates. If you see x squared plus y squared plus z squared, then think about the spherical coordinates. Then you might use the angle phi and theta. Okay? So that is the parameterization for surfaces. Okay, so let's continue with video B, and then I'm going to talk about surface integral for a scalar value function. See you soon!